Okay. Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech, where we go through the Bitcoin Optech newsletter. And this week we will be going through newsletter number 320, published on 13th of September 2024. Uh, as every week, the newsletter is bifurcated primarily into the news article and the code review club and releases and release candidates, notable code and documentation changes. So everything is what we have every week, but the special edition is the review club, which is probably which is a monthly edition. And this week, the review club is about testing Bitcoin Core 28.0 release candidate, and we will probably spend a majority of our time discussing this, and might even spend the entire session discussing about this. This is pretty, I won't say detailed, but a lot of new features have been added, so we can discuss them, and it might probably take an hour. So we will start with this, but before that, I will go through the preface of the newsletter. This week's newsletter announces a new testing tool for Bitcoin Core and briefly describes a DLC-based loan contract. Also included are our regular sections summarizing a Bitcoin Core PR review club, announcing new releases and release candidates, and describing notable changes to popular Bitcoin infrastructure software. The first news article is about mutation testing for Bitcoin Core. The second is about DLC-based loan contract execution. But we will commence with the PR review club session. Any new joinees? All right, fine, cool. Okay, so we will, let's read this before actually digging into the 28.0 release candidate. In this monthly section, we summarize a recent Bitcoin Core PR review club meeting. Testing Bitcoin Core 28.0 release candidates was a review club meeting that did not review a particular PR, but rather was a group testing effort. Before each major Bitcoin Core release, extensive testing by the community is considered essential. For this reason, a volunteer writes a testing guide for a release candidate so that as many people as possible can productively test without having to independently ascertain what's new or change in the release and reinvent the various set of steps to test these features or changes. Testing can be difficult because when one encounters unexpected behavior, it's often unclear if it's due to an actual bug or if the tester is making a mistake. Very true. It wastes developers' time to report bugs to them that aren't real bugs. To mitigate these problems and promote testing efforts, a review club meeting is held for a particular release candidate, in this instance 28.0 RC1. The 28.0 release candidate testing guide was written by Arprox, who also hosted the review club meeting. Attendees were also encouraged to get testing ideas by reading the 28.0 release notes. This review club covered the introduction of testnet 4, truck transactions, package RBF, and conflicting mempool transactions. Other topics in the guide but not covered in the meeting include mempool full RBF by default, pay to anchor spending, and a new dump TX outset format. All right, so generally what happens is in review clubs, a specific PR is taken and that PR is reviewed and tested. But what happened in this case is that because Bitcoin Core's next major release is going to be version 28.0, and it has a lot of features. So that is why an entire testing guide was created by a volunteer for the release candidate of 28.0 so that major features of this release candidate can be tested by a group of people. And this is a general practice. Whenever a major release or a major version of Bitcoin Core is about to get released, a release candidate comes out first, and people are encouraged to test and find bugs before the version of the client goes out for the mainnet and people start using it in production. So what are the main features that have been added in the latest version 28.0? Some of them are mentioned here: testnet 4, truck transactions, package RBF, conflicting mempool transactions, mempool full RBF, pay to anchor outputs, and dump cakes outset. And we've discussed almost all of these things. Uh, during our preceding sessions. So now let's look at the testing guides and try and go through each one of them to the best of our ability as much as time permits us.
One quick point, I think Arcrux is an Indian developer, to the best of my awareness.
I
I
don't
just
know
wanted
who
to pick
he
that
is.
up.
All right. No, I don't
He's a
know who he is.
pseudonym.
Yeah. Sorry, I'm not
Yeah.
aware about that. Okay. All right. So this is the testing guide that has been provided for those who've not already tested and intend to test it. This is the testing guide, and these are the primary features that you have to test. So we'll commence with testnet 4. All right. What is testnet 4? Okay. So here we have the testing guide for testnet 4. Let's go through the BIP first in brief. That contains information about testnet 4. So the BIP is 94, and the title is testnet 4, and the author is Fabian Jar. So a new test network with the goal to replace testnet 3. This network comes with small but important improvements of the consensus rules that should make it impractical to attack the network using only CPU mining. So we're all familiar with what testnet is. It's a network, as the name suggests, which is for the purpose of testing. So when features are deployed on the mainnet, prior to that, they are tested on the testnet, which simulates the behavior of the mainnet. The primary difference being that the difficulty of mining on the testnet is exponentially low and less as compared to the difficulty of testing on the mainnet. So on the mainnet, it's not practical and feasible for you to mine using a CPU, whereas on a testnet, you can mine using a CPU. Rather, it's encouraged that you use a mining a CPU. So that's what testnet is. And up till now, we were using testnet 3, okay? And now we have access to testnet 4. What's new in testnet 4? Consensus of testnet 4 follows the same rules as mainnet with the exception of 3 rules detailed below. Okay, so testnet has consensus rules just like the mainnet has consensus rules. And let us just go through some of the rules. So if you come to Bitcoin Core, you will find this file called chainparams.cpp, where you will find consensus rules pertaining different chains. So you will find consensus rules pertaining the mainnet, pertaining the testnet, pertaining signet, and pertaining the regtest. So currently, because we're dealing with testnet, as you can see, you will find a lot of consensus rules over here. Like for instance, the end subsidy halving interval. All right, I zoomed it a little. So the halving interval for testnet is what? This much. That is 2100,000 blocks. So you can see. And the difficulty adjustment period is the target difficulty adjustment period, not the actual, okay, because the actual is dynamically calculated, but this is the target. The target is 2 weeks. That is 14 days, each comprising of 24 hours, each are comprising of 60 minutes, and each minute comprising of 60 seconds. And the target spacing between two blocks, this is the ideal or the targeted spacing between two blocks, that is 10 minutes of 60 seconds each. And you can find a lot of other information pertaining the consensus rules of Signet. As you can see, allow minimum difficulty blocks. So we've talked about what minimum difficulty blocks are, right? And the minimum difficulty for testnet is 1. So it's set to true. So minimum difficulty blocks are allowed in the testnet. And there are a lot of other things as well pertaining to testnet. So if you'd like to go through them, this is the place that you need to come to chainparams.cpp. Now, there are 3 notable changes in testnet 4 that we will go through. The first is 20-minute exception. The second is a block storm fix. And the third is time warp fix. Now, what's a 20-minute exception? This rule was already previously implemented and active in testnet 3. So this rule was incorporated in testnet 3 and now it's being carried forward to testnet 4. A block with a timestamp that is more than 20 minutes past the timestamp of the previous block must have a minimum difficulty of 1, the network's minimum difficulty, instead of whatever the actual difficulty level currently is. This applies to all blocks in a difficulty period except for the first block. So what this rule states is that on the testnet, when um, the timestamp of a block is more than 20 minutes past the timestamp of the previous block, the difficulty of mining that block goes down to the minimum difficulty. That's one. So when there is a block which has a timestamp which is 20 minutes past the previous confirmed block on the test net, then the difficulty of mining that block will come down to one, irrelevant of what the network difficulty is, irrelevant of what the network hash rate is. All right, because the purpose of having a test net is obviously to test things. And if a block is not getting mined for a longer tenure of time, then it becomes difficult for developers and researchers to test. And that is why this rule was incorporated in the testnet that if there is a block which has a timestamp 20 minutes uh, past the timestamp of the previous block, then the difficulty of mining that block, that candidate block, will come down to one, and the block will be mined immediately so that the testing does not get hindered. All right. So this is one primary difference in testnet 4, or noteworthy change in testnet 4. Although this was incorporated recently in testnet 3, it's being carried forward to testnet 4. The second notable upgrade is the block storm fix. What's a block storm? As the name suggests, storms of block. So on testnet, this is quite a common phenomena that blocks are mined in quick succession, right, one after the other, and this phenomena is known as a block storm. The work required for a new difficulty period is calculated as a multiplication factor to the difficulty of the previous period, but no less than one-fourth and no more than 4x, depending on the duration of the previous difficulty period on mainnet and testnet. 3. This factor is applied to the difficulty value of the last block. So we know that the difficulty adjustment period is of 2016 blocks, and the difficulty of the previous period is an inferential factor, or is the factor that determines the difficulty of the subsequent factor. Now, the difficulty of mining blocks in a difficulty adjustment period cannot go up exponentially, neither can it go down exponentially. There is a range within which it can increase and it can decrease. So the difficulty after one difficulty adjustment period can increase maximum by 4x, or can go down by one-fourth. So if for a period of 2016 blocks, the difficulty of the Bitcoin network was X, then for the next 2016 blocks, it can either go up to 4x, increase by a ratio of 4, or it can go down by one-fourth, not more than that, at least in a subsequent period. Block storms happen organically whenever the 20-minute exception is applied to a difficulty period's last block, causing the block to be mined at a difficulty of 1. The difficulty adjustment rules then limit the subsequent period's difficulty to a value between 1 and 4. So the difficulty is calculated based on the difficulty, or the difficulty of a difficulty adjustment period is calculated based on the difficulty of mining the last block. Okay, and we just now talked about the 20-minute exception rule. So if the last block in a difficulty adjustment period has a timestamp which is 20 minutes past the previous block, then the difficulty of mining the last block will be 1, right? And if that is 1, then that factor will be taken into consideration, or that will be the benchmark in determining the difficulty of the subsequent difficulty adjustment period. All right, so this way somebody can artificially decrease exponentially the difficulty of mining blocks on the test net uh, uh, by ensuring that the last block that is mined in a difficulty adjustment period has a timestamp of 20 minutes ahead of the past block that has been mined, thereby ensuring that the final block that is mined on the test net has a difficulty of 1, which will then be taken into consideration. And then the difficulty of the subsequent difficulty adjustment period will be between 1 and 4, making the blocks very easy to mine, thereby causing a block storm. Blocks will be generated rapidly in the subsequent low difficulty periods while the difficulty climbs back to an adequate range. An arbitrarily large number of blocks can be generated quickly by repeatedly using the 20-minute exception on every last block of difficulty period. So this behavior can be recurring, because every single time during a difficulty adjustment period, you take the last block and you ensure that its timestamp is is in such a manner that the difficulty of mining that candidate block comes down to 1. And when it comes down to 1, then that affects the difficulty of the subsequent difficulty adjustment period. And you can keep on repeating this phenomenon to generate what we refer to as a block storm. The block storm is then bounded only by minor hash rate, the need for last blocks to have a timestamp 20 minutes after the second to last block, the median time passed and the median time passed end time rule, and the requirement that blocks can't be more than 2 hours in the future. Overall, a sustained attack would eventually be limited to a maximum cadence of 6 blocks per second. A block storm does not require a time warp attack, but one can be used to amplify. So a time warp attack is not a block storm attack. I mean, a time warp attack can cause a block storm attack, but you can execute a block storm by merely using the 20-minute exception rule. You don't necessarily need a time warp attack. Now, what's the mitigation? What's the solution of this? The mitigation consists of no longer applying the adjustment factor to the last block of the previous difficulty period. Instead, the first block of the difficulty period is used as the base. So what we do to fix this problem, we no longer use the last block in the difficulty adjustment period as the criteria or the benchmark to determine the difficulty of the subsequent difficulty adjustment period. Rather, we use the first block. Okay, so we don't use the last block, we use the first block. All right, and how exactly it does using the first block fix it? The first block must contain actual difficulty of the network and can therefore be used as the base for the calculation of the new difficulty level. So just now we studied that the 20-minute exception does not apply to the first block in a difficulty adjustment period. If we can go back to it, this applies to all the blocks in a difficulty period except for the first block. So the first block is immune to this 20-minute exception. All right, the first block will always have a difficulty which is equivalent to the network's actual difficulty. It will not have minimum difficulty just because of the timestamp. It will have an actual difficulty. So the first block in a difficulty adjustment period on the test net is immune to the 20-minute exception rule, meaning even if the timestamp of the first block in a difficulty adjustment period is 20 minutes past the previous block, its difficulty will still not come down to 1 because it's immune to the 20-minute exception rule. Its difficulty will be the same as the network's difficulty. So that is how we mitigate this block storm attack by passing on the onus of determining the difficulty from the last block of a difficulty adjustment period to the first block of the difficulty adjustment period, and then ensuring that the first block is immune to the 20-minute exception rule, meaning the difficulty of the first block cannot be manipulated and will always be judged based on the actual difficulty of the network. All right, we've talked about time warp attacks previously. Okay, if any of you don't know what a time warp attack is, then you can refer to a lot of articles that are available on the internet. It's basically a mechanism in which you manipulate, in which a miner or a group of miners, if they have hash rate in excess of 51%, they can manipulate timestamps to deceive the difficulty adjustment algorithm into believing that it took more time to mine X number of blocks than it actually did, and thereby tricking the difficulty adjustment algorithm to reduce the difficulty of mining blocks. In addition to a time warp attack potentially exacerbating the perpetual block storm attack, a time warp attack provides an alternative way to increase the block production rate even if the unintended reset of the actual difficulty due to the 20-minute exception was mitigated. To protect against a time warp attack, the following rule proposed as part of the Great Consensus cleanup is enforced. The end time field of each block whose height mod 2016 is 0 must be greater than or equal to the end time field of the immediately prior block minus 600 seconds. All right. So there are different ways in which you can perform a time warp attack, one of which is by uh, manipulating the timestamps of the first block in a difficulty adjustment period and putting it in the past. Putting it in the past. Okay, so the timestamps are manipulated in such a way that the block's time is preceded. It's put in the past. You can put it 2 weeks in the past, 4 weeks in the past, even 8 weeks in the past. All right. Now we know that there is a threshold for which timestamps are valid. The lower threshold is the median time passed of the previous 11 blocks, and the upper threshold is 2 hours plus the current time. But the timestamps are manipulated in such a way that despite abiding by this rule, you can manipulate the timestamp of a block and put it into 2 weeks in the past, 4 weeks in the past, even 8 weeks in the past. And how that can happen, you can read a lot of articles or a lot of material that is available on the internet, on the dev mailing list, on Bitcoin Stack Exchange, on the Optech newsletter. And we also have covered it on various occasions. So you can also refer to Bitshala's YouTube channel and refer to our previous sessions where we've talked about this in detail. Now, how do we mitigate it? We mitigate it by applying this rule that the first block in a difficulty adjustment period cannot have a timestamp which is 600 seconds behind the timestamp of the previous block which has been mined. Okay, so you take the timestamp of the last block that has been mined in a difficulty adjustment period, and you take the timestamp of the first block that has been mined in the subsequent difficulty adjustment period. So the timestamp of this first block cannot be more than 600 minutes in the past, meaning it cannot be more than 600 seconds. Sorry, it cannot be more than 600 seconds before the timestamp of the last block of the previous difficulty adjustment algorithm. By this, what do you do? By doing this, you ensure that nobody can artificially manipulate the timestamps of the first block in a difficulty adjustment period to 2 weeks in the past, or 4 weeks in the past, or 8 weeks in the past, which is one of the most potent ways of executing time warp attacks. You ensure that the timestamp of the first block in the difficulty adjustment period is either the actual timestamp or at the most 10 minutes behind the timestamp of the previous mine block. So this is how you fix a time warp attack. So we discussed what a testnet is. We discussed what testnet 4 is, and we touched upon three main features or talking points of the 20 minute of testnet 4. The first being 20-minute exception, the second being block storm fix, and the third being time warp fix. Now let's just briefly go through to see how we can test it, how we can test testnet 4. So what you can do is you can download the release candidate of Bitcoin Core version 28.0, or depending on when you're listening to this, if it's available on mainnet, then you can do that. Go and download the production version of the client. And all you have to do is go to your bitcoin.conf file and set this flag testnet 4 equals to 1. So all the clients before 28 have access to testnet 1, testnet 2, and testnet 3, depending on when they were released. But it's only 28 and above that will have access to testnet 4. All right. So if, for instance, you are using Bitcoin Core's version 27.1 and you try and set this flag will not be activated because testnet 4 is not compatible with testnet with any client preceding 28.0. So if you are testing the release candidate of Bitcoin Core version 28.0, or you are using it in production, the best way to test testnet is by going to your bitcoin.conf file, set this flag, okay, and then what do? Then you run your node and then you give it this command, okay, this RPC command, get blockchain info. When you issue this command, get blockchain info, you will get info pertaining the chain, pertaining the blockchain, and the chain parameter will have a value testnet 4, which signifies that you are running a client version which is compatible with testnet 4, and testnet 4 has been activated. So this is one of the ways of ensuring or testing testnet 4. And then you can create wallets, and then you can go to faucets and get coins, and send coins and receive coins, and do a lot of other testing and check its use cases. So this is what we had to share about what testnet is, what testnet 4 is, what primary features and upgrades or noteworthy points of discussion it contains, and how you can check whether the client that you are using is compatible with testnet 4 or no. So if any questions, any queries, any thoughts, any anecdotes pertaining testnet 4, please feel free to unmute yourself and talk, or type in the chat before we move on to the next feature of Bitcoin Core 28.0. Something in the chat. Need to drop off. Good night. No worries. Mango doesn't even message, he just drops off. At least share messages.
Hi, Faisal.
Hey,
Sorry,
hi.
yes, sorry, I joined a little bit late, but I'm trying to understand um, what's the average time, what's the target average time for mining a block in testnet 4? I'm asking that
10 minutes.
because, okay, 10 minutes. Okay, great. All right, thank
Yeah,
you.
we just went through it. I think it came late. All right. So if you go to Bitcoin Core, there is this file in Bitcoin Core. If you go to the source folder, you will find this file called chainparams.cpp. Here you will find all the consensus rules pertaining all the four nets. Okay, mainnet, testnet, signet. So if you see, we'll go through it in brief. So here you'll find the consensus rules for the mainnet. Okay, as you can see, main. All
All right.
right. And you see the target spacing is 10 into 60. So that is 10 minutes, each minute of 60 seconds, right? So that's 600 seconds or 10 minutes. So the
All
ideal time between two blocks on the mainnet is this 10 minutes. And now if you scroll down, you will go to testnet. Let me see where this test. Yeah, okay. So here are the consensus rules for testnet. And if you see
right.
if the same rule is for testnet,
Okay,
target
okay,
spacing
great.
is 10 minutes of 60 seconds. All right.
All right, thank you.
Yeah, you're welcome. All right, anything else? If nothing, let's move on to the second feature. All right, so now let's talk about truck transactions or V3 transactions. Truck transactions known as topologically restricted until confirmed a transaction. So these are in addition to the latest version of Bitcoin Core, which currently is version 28.0. Let us briefly go through what transactions are, what their attributes are, what their features are, what new do they bring for Bitcoin users. So, uh, transactions with version number set to 3 are now treated as standard on all networks. All right. So up till now, we had transactions with version number 1 and version number 2, which were treated as standard transactions on the Bitcoin network. So if you look at the hexadecimal output of any Bitcoin transaction that starts with version number 01 or version number 2, then that is a standard transaction. And other than that, it was considered a non-standard transaction. But now transactions with version number 3 are considered also as standard transactions in Bitcoin. All right. As I just mentioned, truck transactions are transactions that have a version number 3 and they are known as topologically restricted until confirmation transactions. All right. So this is the BIP that will give us more information into what truck transactions are. Let's just read and go through and understand some of the attributes or features of V3 transactions that make them different, which will also help us understand their usability. The version number is 3. So whenever you see a transaction with version number 3, then that is a truck transaction or a V3 transaction, which is now a standard transaction. Senders can signal that they want a transaction to be topologically restricted until confirmation. Specifically set n version equals to 3, a node that implements this policy would apply their existing standardness and policy rules along with the following set of rules. So all the policy rules that are for version 1 and 2 are also applicable to version 3. Along with that, version 3 comes with its own new sets of policy rules. Now, what are they? A truck transaction signals replaceability even if it does not signal BIP 125 replaceability. So up till now, if we wanted to RBF a transaction, we had to signal for it. So while you are creating a transaction, you have to curate the transaction in a manner that it signals replaceability, which is governed by BIP 125. If you create a transaction of version 1 of or version 2, which does not signal replaceability, you cannot replace that transaction once you have created that transaction, once you've signed that transaction and you've broadcasted that transaction, you cannot replace that transaction until and unless you had predefined that it is eligible for being replaceable. How do truck transactions or version 3 transactions differ? They are replaceable by default. So there is no need for you to signal for replaceability. Truck transactions of themselves are replaceable. So any transaction that has a version number 3 is replaceable. There is no need for you to signal it specifically. Any truck transactions, unconfirmed ancestors must all be trucked. Okay, so any transaction with version number 3, if it has unconfirmed ancestors, even their version number should be 3. Okay, confirmed ancestors can have any version number, but unconfirmed ancestors can have only version number 3. So a truck transaction can have only unconfirmed truck ancestors. A V3 transaction, a transaction with version 3, can have only unconfirmed ancestors with version number 3. And same goes for descendants. Any descendant of an unconfirmed truck transaction must also be a truck transaction. Note, a truck transaction can spend outputs from confirmed non-truck transactions. Okay, so a truck transaction can have ancestors which are non-truck, meaning which can have a version number other than 3, which can have a version number, for instance, 1 or 2, the condition being they are confirmed. So a truck transaction can have parents or ancestors which are non-truck, but the condition being they are confirmed. If they're unconfirmed, they have to be truck. A truck transaction can have only truck ancestors if they're unconfirmed, but if its ancestors are confirmed, then they can be truck and they can be non-truck. Same goes for descendants. A truck transaction can only have unconfirmed truck descendants, but if the descendants, a non-truck transaction can spend outputs from confirmed truck transactions. So a non-truck transaction can spend outputs from confirmed truck transactions. So a truck transaction which is not yet confirmed, it can spend outputs from a truck transaction which is confirmed. All right. The third attribute is an unconfirmed truck transaction cannot have more than one unconfirmed ancestor. An unconfirmed truck transaction cannot have more than one unconfirmed descendant. All right. So this is what we refer to as one parent, one child topology, meaning a truck transaction can have only one child. It can have only one child as long as uh, uh, and it can have only one ancestor, meaning one parent, as long as it's unconfirmed. So a truck transaction cannot have more than one unconfirmed ancestor, and an unconfirmed truck transaction cannot have more than one unconfirmed descendant. CPFP carve-out is not granted to truck transactions. What CPFP carve-out? It's a mechanism for mitigating pinning. It is primarily used on pre-signed transactions like the commitment transaction on the Lightning Network. So up till now, we had a topology uh, where a transaction is not eligible to enter the mempool if it has 25 or more unconfirmed ancestors already in the mempool. Okay, so it's possible that one party in the Lightning Network might want to pin the other party, and to do that, what do? They add 25 descendants to the commitment transaction. Okay, 25 uh, 25 low fee rate transactions. Now, what this can do is this can prevent the other party from opting out of the contract, and they cannot add a child to bump the fee of the commitment transaction, because now already 25 unconfirmed children have been attached to the commitment transaction. Now you cannot add one more. So what CPFP carve out does is that it mitigates or it circumvents that 25 transaction rule and allows one more. It makes the rule of 25. It relaxes the rule of 25 transactions, takes it to 26. So like we've discussed about this in detail in our preceding sessions, and you can also refer to what a CPFP carve out is, what transaction pinning is, what commitment transactions on the Lightning Network are. You'll find a lot of resources on the internet, on Bitcoin Stack Exchange, on Dev mailing list, and even on um, the YouTube channel of Bitshala. So the point being, now that we have reached a stage where truck transactions can have a one parent, one child topology, right? So one unconfirmed truck transaction can have only one unconfirmed descendant, or it can have only one unconfirmed ancestor. So we have a one parent, one child topology. So the question of having 25 children or 26 children is now ruled out. So CPFP carve out is not granted to truck transactions, obviously, because truck transactions cannot have 25 unconfirmed descendants. What's the fourth? A truck transaction cannot have a SIGOP adjusted virtual size larger than 10,000 virtual bytes. So a truck transaction is limited to a certain size. A truck transaction or a V3 transaction or a transaction with version number 3 cannot be greater than 10,000 virtual bytes in size. A truck transaction that has an unconfirmed truck ancestor cannot have a SIGOP adjusted virtual size larger than 1,000 virtual bytes. So it's if there is a truck transaction that has an unconfirmed truck ancestor, then that truck transaction cannot be more than 1,000 virtual bytes. So if we have one parent and one child, the parent is truck, the child is truck. The parent is unconfirmed, the child is unconfirmed. In this situation, the parent cannot be more than 10,000 virtual bytes, and the child cannot be more than 1,000 virtual bytes. All right, an individual truck transaction is permitted below be below the mempool min relay fee, assuming it is considered within a package that meets the mempool's fee rate requirement. So, like every mempool has a minimum relay fee rate. All right. So a transaction needs to pay at least that amount of fee for it to be included in the mempool. But truck transactions are an exception. Why are they exception? They are exception because they allow package relay. So even if a truck transaction is paying a fee which is so low that it is not eligible to be included in the mempool, its child can be attached to it. And if the child pays a high fee, then the entire package of truck transactions of the child and the parent, one child, one parent package of two transactions, if both of them together, if this package together pays a fee which is above the minimum relay fee rate, then that package together is eligible to be included in the mempool. So these are six major attributes of truck transactions and how they differ from the version 1 and the version 2 transactions. Now let's just go and see what we can make of them, like how can we avail the benefits of them. All right. So what you can do is if you are running Bitcoin Core version 28.0, uh, either the release candidate or depending upon when you hear this, the production version. All right, what you do is when you run your Bitcoin node, you specify mempool full RBF0 because Bitcoin Core versions 28.0 onwards will have features for uh, which will enable transactions to be replaced by fee by default, meaning you don't need to signal you don't require the web 125 signaling. All right, you just have to set this flag as 1 and by default the transactions will be eligible to be replaced. So intentionally we're declaring this as 0. All right, so when we declare this as 0, then version 1 and version 2 transactions by default cannot be replaced. Only version 3 transactions can be replaced, right? Because for version 3 neither do you need to enable this flag nor do you need to signal for BIP125 replaceability. And we want to test whether truck transactions are replaceable by default, even without signaling and even without enabling this flag. So we will not signal for BIP125 replaceability, and we will even ensure that this flag is set to 0. And then we'll check whether we can replace truck transactions or V3 transactions. So what do you do for that? All right, you uh, get mempool info to ensure that your full RBF is false, meaning this is set to 0. Once you've ensured that, you create a test wallet. All right, you mine some coins. So now you have some balance. You check your unspent UTXOs or your unspent transactions. You select any transaction from the available unspent transactions that you have in your wallet. What do you do that? Then you create a new address. Okay. Now you create a new transaction without BIP 125 signaling. Okay. Notice the false flag at the end that unsets BIP 125 signaling. So now you create a transaction. You took a TXID and unspent TXID from your wallet, and now you're creating a transaction. This is how you create a transaction. Most people use modern wallets. The wallet does it for you. But if you ever happen to handcraft a transaction, this is how you do it. TXID follows by the V out, meaning the output, and 0 means the first output. This is the address, BCRT. This is the address to which you're spending, and this is the amount that you're spending. All right. So out of 50, if you spend 49.99999, the remaining is fee, which is paid to the miner, and your false means you are not signaling BIP 125 replaceability. All right. Once you create this transaction, this is your TXID. Now remember that this is a version 2 transaction, right? As you can see, as the advent of the transactions hex dump, you can see 02, which means it's a version 2 transaction. Up till now, it's not version 3. What do we have to do to convert it into version 3? It's very simple. Just replace 02 by 03. Okay, so everything is the same. 17C3, 17C3, everything is the same. We just take this and we replace it with 3. So version 2 becomes version 3. Okay, that's what we do. Now we sign this transaction. Once we have signed the transaction, we send the transaction, meaning we broadcast that transaction. Once we broadcasted the transaction, it enters the mempool. This is the TXID of the transaction that we've broadcasted. Once we broadcasted it, it enters the mempool. Okay, now using this TXID and this RPC command, we can check whether this transaction is in the mempool. All right, so we check whether this transaction is in the mempool, and this is the output that we get. All right, so the transaction is loaded true, meaning it is in the mempool and it does not signal for BIP 125 replaceability, nor does it set the mempool full RBF flag as 1. Now what are we going to do? Now fetch this in wallet transaction using get transaction and check BIP 125 replaceable property in the output. Okay, so we fetch that transaction And here we ensure that it is not BIP 125 replaceable. So here we ensure that it's not BIP 125 replaceable. Okay, using this RPC command, get transaction, it tells you that this transaction that is in the mempool is not replaceable. And above, we already ensure that full RBF is default. So we are making sure that full RBF, mempool full RBF is disabled, and also we've not signaled for BIP 125 replaceability. Despite that, we will replace this transaction and prove that truck transactions or version 3 transactions can be replaced by default without signaling or without enabling the mempool full RBF. Now, how do we do that? That's the third step. Replace V3 transactions without a BIP 125 signaling while running the node with mempool full RBF 0. We've done all of that. Now that we have a V3 transaction in the mempool that has not signaled for RBF, let's create a new transaction that double spends this one by spending the same input used. Okay, so now what we will do is we will use the inputs of the same transaction that we already have in our mempool. Okay, we'll try and double spend it, but this time with a higher fees. So now we have two competing or conflicting transactions, both having the same inputs, both V3, but one paying the higher fee, and we'll prove that the one that pays the higher fee will be accepted and the one that pays the lower fee will be rejected, and hence we will prove that V3 transactions, even without BIP 125 replaceability, even with a mempool full RBF being disabled, are replaceable based on the fee. What do? We create another raw transaction. Okay, we use the TXID and the output is 0, and we take the address and the fee. Okay, so this time it's paying a higher fee. Last time it was 99999. This time it's 99995, meaning the replacement pays a higher fee. That's a prerequisite. Only if you're paying a higher fee will the miners be incentivized to replace the latter transaction with the former transaction. And then you sign that transaction. Okay, and then after that, what do? You send it. Okay, you broadcast it to the network. It goes into your mempool. This is your TXID. This is your TXID. Now use the get transaction to fetch this in wallet transaction. Notice the wallet conflicts property of the output that contains the previous transaction that has been replaced by this one. Okay, so you use this RPC command, pass it your TXID that we received over here after sending the transaction. What do you see? Your wallet conflicts. It shows that it conflicts with this transaction. It shows that it conflicts with this transaction. All right, and this transaction will now be included in the mempool, and the previous transaction will get rejected from the mempool because this transaction pays a higher fee. So this is how you can ascertain that V3 transactions are replaceable even without signaling for RBF and even without enabling mempool for RBF. Now, another attribute of V3 transactions is sibling eviction. We'll not go into it in a lot of detail. We've talked about it excessively in preceding sessions. What is sibling eviction? Assume a parent transaction that has two outputs. Okay, so for testing this feature, we will create a parent transaction. So there's this parent transaction TX having two outputs. Okay, and then subsequently create a child transaction sibling TX1 spending the first output of the parent transaction. We will then send both these transactions and they should be accepted in the mempool. Later, we will create another child transaction sibling TX2 of the parent. So you have a parent transaction that has two outputs. Okay, now you create a child for one of those outputs and you call it sibling TX1. Okay, and you create that transaction and you broadcast that transaction. Then what do? Then you take the second output of the same parent transaction and you attach another child transaction to it with a higher fee. Okay, with a higher fee. What will happen in this situation is that this set of transaction that has sibling transaction 2 will replace sibling transaction 1. Now what is noteworthy here? First thing that is noteworthy here is that without again signaling for BEP 125 or enabling the mempool full RBF flag, we were able to replace transactions, which previously was not possible. Second thing, if you see, is that these are transactions that are not directly conflicting with each other, right? These are at the same hierarchy. These are siblings. And one sibling, despite not in and of itself contradicting with the other sibling, is able to replace it, which was not possible earlier. All right. We will then send both these transactions and they should be accepted in the mempool. Later, we will create another child transaction sibling TX2 of the parent transaction by spending its second output but with higher fee. This would become a sibling of the first child transaction. Also, we will create a child transaction TX with uncle. Okay, so this is the first thing that we can experiment with, or first observation of sibling eviction, meaning transactions that are at the same hierarchical level and do not conflict with each other per se. Okay, this sibling transaction has another parent, and this sibling transaction has another parent, right? They're spending different unconfirmed UTXOs of the parent TX. Despite that, one sibling is able to replace the another sibling despite being at the same hierarchical level. Now, this has a very important use case in pre-signed transactions, okay, in mitigating pinning attack on the Lightning Network. One more thing that we can notice is TX with uncle. All right. So we have a parent transaction and it has two outputs. Okay. And both those outputs are unconfirmed. Then we attach a child to it, sibling transaction two. Then we attach another child to it. We call it TX with uncle. So this topology now has three unconfirmed transactions. And up till now, we've studied that V3 transactions have a topology of one parent, one child, meaning they can have only one parent and one child, one unconfirmed parent and one unconfirmed child too. They cannot have more than I mean the package cannot have more than two transactions. But for testing purpose, we'll attach a third one here. We'll call it TX uncle, and then we will broadcast that transaction, all right, to the mempool. And once we broadcast that transaction to the mempool, I'm kind of fast forwarding here, but the point being, it will fail. It will fail, all right? So when you create a parent transaction, it has two unconfirmed outputs. You create a child for that unconfirmed output, and then you attach another transaction, unconfirmed transaction to that child, and you create a topology of three transactions in succession. It will fail. Okay, and what's the reason? Truck violation. So truck transactions or V3 transactions can have only one child. Okay, so one unconfirmed truck transaction can have only one ascendant, and one unconfirmed truck transaction can have only one descendant. Here, what we're doing is we are trying to create a topology of three transactions, one, two, three, and then we are trying to broadcast that transaction and it fails. So we can validate this property of V3 transactions as well. So these are what truck transactions or V3 transactions are. We discussed some of the important attributes and features of them, and we discussed some use cases of them, and we saw some tests that ensure that the features that we have discussed can be actually practiced, implemented, and tested by the end users as well. So if anybody has any specific questions about V3 transactions, please feel free to unmute yourself and ask them or post in the chat section.
Yeah, so I'm guessing that V3 transactions, they take the structure of segregated witness, right?
Yes, they do. V2 and V3 both. V1 don't. If you see a transaction with version number one, it's a pre-segwit transaction. If you see a transaction with version number two or three, it's a segwit transaction.
Okay, all right. Thank you.
Could you please elaborate why siblings replace each other if they do not conflict? Couldn't they both be confirmed? Yes, they can absolutely both be confirmed, but this has a use case on the Lightning Network. This has a use case on the Lightning Network. So basically, what happens in the Lightning Network is, right, the Lightning channel is between two people. Okay, it's between Alice and Bob. All right. Now, Alice wants to close the channel, but Bob does not want to close the channel for some reason, or Bob is acting rogue. Now, what Bob can do is that if the commitment transaction, so the commitment transaction on the Lightning Network is a transaction with which you move out of the transaction. Okay, so there are only two on-chain transactions in the Lightning Network. The first is known as the funding transaction with which you start a lightning channel. The last is known as the commitment transaction with which you end on the with which you end the channel. All right, so only these two transactions are recorded on the blockchain. Everything else happens on layer 2. Now what happens is that your commitment transactions are pre-signed. Okay, because when you set up a a lightning channel, you don't know when you close that lightning, sorry, you don't know when you close that lightning channel what will be the fee, right? You can't predict it. So you pre-sign a transaction which is known as a commitment transaction, that hey, when we decide to close this lightning channel, we will close it on such and such terms. Let's already sign a commitment transaction. Now when you are actually closing the lightning channel, maybe you start a lightning channel and you close it 2 months later, and in 2 months the fee market has gone absurd, and you agreed upon a fee of 2 sats for virtual bytes, but now it's 10 sats for virtual bytes. So obviously that transaction will not get confirmed. So for that reason, you can attach a child to your commitment transaction and bump the fee of the commitment transaction. Okay, now what if your commitment transaction is a V3 transaction? The commitment transaction is unconfirmed and it's a V3 transaction, meaning it can have only one child attached to it, right? We already studied now that a V3 transaction which is unconfirmed can have only one child. So Alice does not want Bob to opt out of this lightning channel. Alice wants to harass Bob for whatever reason. What Alice can do is Alice will attach one child to the commitment transaction. Okay, and that child will pay a very low fee. The child will pay a very low fee, and that is why the miners will not get incentivized to broadcast that to mine that transaction. All right, and now because we know that a V3 transaction can have only one child, in this situation, what Bob can do is Bob can attach a sibling to it. Bob can attach a sibling to it. All right. So let's assume that this is the commitment transaction. Alice attaches one child to it, which pays a very low fee. So the miners are not incentivized to mine this transaction. Now, what Bob will do is Bob will attach a sibling. Bob will attach a sibling to it. Now, the sibling is paying a higher fee. All right. So there is no reason for this transaction to go on the chain, right? There is no reason for this transaction to go on chain. This transaction has been attached by Alice only to ensure this is a very low fee transaction, and it's been attached by Alice only to ensure that this package does not get mined and Bob is harassed. All right. Once Bob attaches a sibling with a high fee to ensure that this parent transaction and the sibling gets mined, there is no need for this data to go on the blockchain. This is redundant data, right? So we can evict this. There is no use case for this, right? Alice genuinely does not want to use this transaction, right? Alice has just attached this transaction to harass Bob, to pin Bob. That is what we call a pinning attack, right? So Alice has attached this transaction to pin Bob. That is what she's done. She's attached this transaction just to ensure that this never gets mined and Bob keeps on suffering. But now what Bob will do is Bob will attach another transaction to it. Okay, it's a V3 transaction. Once Bob attaches this transaction, this diagonal topology of parent and sibling 2 is now luring enough and incentivizing enough for the miners. So the miners will choose this parent TX and sibling TX2. Now there is no reason for this transaction, right? Without any reason, we don't want to burden the blockchain because we don't want additional data on the blockchain. We don't want additional UTXOs in the UTXO set because it becomes difficult to run a node. What we can do is we can just get rid of the sibling transaction whose only purpose was to harass Bob, and we kick this transaction out and we take this one and this two and we mine this transaction. So this is what is known as sibling eviction. I hope this answers the question. All right, fine. Just give me a minute. We've talked about sibling eviction in detail, in a lot of detail. So maybe if on YouTube, if you can find our videos, because generally when we upload videos, we add text to those videos so that it's easier to find. And if even if you don't find it, then you'll find a lot of content. You can go to Delving Bitcoin and understand how Lightning channels function, what commitment transactions are, what pinning attack is, what CPFP carve out is, what anchor outputs are, what truck transactions are, what sibling eviction is. Like around 4 to 5 months ago, 3 to 4 months ago, we talked a lot about it. And back then, many like I can see many new faces here, so maybe you all must have missed it out. But those who have been attending our sessions January onwards, then it's just like a continuity of what we've discussed. So yeah, we are at 8:59. What can we cover now? Can we take one more thing? One more thing quickly. What can we take? Yeah, we can take package RBF. We can take package RBF and then we can call it a day. All right. Yeah, all right. Let's understand what is a package RBF. Limited package RBF is now enabled where the proposed conflicting package would result in a connected component, also known as cluster, of size 2 in the mempool. All clusters being conflicted against must be of size 2 or lower. So up till now, we have known the concept of one transaction replacing the other transaction. All right. So one transaction that is paying a low fee can uh, get replaced by another conflicting transaction that pays a higher fee. All right. Now there is more to it, but I'm just discussing on the surface level. Now we have this concept of package RBF, meaning a package of transactions can be replaced by a package of another transaction. but this topology is restricted to what? Size 2. A package of two transactions, meaning one parent, one child, can now be replaced by a package of another transaction, meaning one parent, one child, using the same rules of individual transactions replacement. How do we understand this? We understand this by going through this process. It's pretty straightforward. Firstly, we will create a package of a parent and a child transaction and submit it in the mempool, and it should be accepted. All right. So the first thing we do to test this is we create a package. We create a parent and a child, and we submit it to the mempool. Later, we will create another package of parent and child transaction where the new parent double spends the input of the first parent to make them conflicting with each other. So we already create a package and we broadcast it and it's already in the mempool. Now we'll create another parent which double spends the inputs of the first parent or the earlier parent that we created. All right. So, and then that parent will have a child. So now we have two conflicting packages, one package of a parent and a child, and the other package of a parent and the child. And both the parents spend the same inputs, meaning these two packages are conflicting. Both of them cannot be mined at the same time. Only one of them is acceptable. And the criteria based on which we choose which one is acceptable is what? Is the fee. The child of this new package will have higher fees than the child of the previous package, due to which this new package would be accepted in the mempool while replacing the first package. All right. So for testing purpose, you can go to your node and access the list of your unspent transactions. When you generate a new address, so what do you do after that? You create a transaction. All right. So you create a transaction with the TX ID and the address to which you want to send. This is the first parent transaction. All right. When you sign the parent transaction, all right. And then what do? You create a child transaction. You create a child transaction for that parent transaction and you sign the child transaction as well. Then you test mempool accept. All right. Then you test whether this package is eligible to enter the mempool. Up till now, we're familiar with the concept of sending individual transactions to the mempool. But now we have to familiarize ourselves with the concept of sending packages to the mempool. All right. So how do we do that? We use this command test mempool accept. All right, and we pass the relevant information to it. Now, one thing that is noteworthy over here is you can see we are testing two, right? If you want to test whether a transaction is acceptable or eligible to enter the mempool, we will pass what? We will pass it one value of that transaction, right? The hexadecimal dump of that specific transaction. But here, what is noteworthy is that we are trying to send the entire package. We are trying to send the entire package to mempool, so we have to test for the eligibility of the entire package. So we're using both the transactions. So up to here, this is the parent and this is the child. So all right, we pass both the values, both the hexadecimal outputs of the child and the parent, and then is it allowed or is it not allowed? It's allowed. All right, so this package is allowed. Then once it's allowed, what do? We submit the package using submit package. All right, we submit both the parent and the child. So now we have a parent and a child package, which is in the mempool. Now what do? We create another address and we create a new parent. Okay, and that spends the same unspent of the first parent transaction. So we create a new transaction. Okay, we use this. We use, but in this new parent, we use the same unspent of the first parent transaction. All right. So to ensure that both the packages conflict with each other, then we sign that parent transaction. Okay, then create a new child transaction of this new parent transaction, but with higher fee. So we create child as we created earlier, okay, and then we sign that child, okay, but we pay a higher fee than it. So while creating the transaction, let us see if we can see the fee. You see it's paying a higher fee. So earlier it was paying 49.99999. Now it's paying 49.99995. So we're paying a higher fee. So the second package pays a higher fee than the first package. Now test the mempool acceptance like we did the last time. We take the parent and the child and we see if this package is eligible to enter the mempool. And what do we get now? It says false. It says false. All right, because it's not BIP 125 replaceable yet. Note the current status of the mempool. It contains the transactions of the previous package at the moment. All right. Get raw mempool. This will give us the list of transactions that are in the mempool. Submit the new package to the mempool and note that the transaction of the previous package are replaced by the ones in the new package. So you submit it. All right. So when you test for it, it'll say false because already a transaction exists in the mempool. But when you submit it, the transaction that is paying the higher fee will be accepted in the mempool. So success. So what happened here is that we created two packages. What's the concept of a package RBF? All right, up till now we were familiar with the concept of transactions RBF, where one transaction, where if two transactions were conflicting each other, then the transaction that paid a higher fee per virtual bytes and higher absolute fee would replace the other transaction, taking other criteria into consideration as well. But now we're talking about package RBF. They're one package, one child, one parent topology package, which is conflicting with another package of two transactions, one child, one parent. The package that pays the higher fee will replace the package that pays the lower fee. This is the concept of package RBF. So we discussed it in brief, and we also went through the commands that will allow us to ensure. So any of you can test this on your reg test mode, or depending upon when you're listening to this, if you have access to this feature in production, then maybe you can create your own transaction. And if you actually want to make a payment, you can test it on the mainnet. So this is what package RBF is all about. Any questions, any thoughts, any comments about package RBF before we wind up the session? Right, guys. So the testing guide is here. I'll share the link. Okay. So those of you who want, there are total 7 to 8 features, but we will not be able to cover all of them. I wanted to cover all of them. I thought I'll be able to cover all of them, but I don't know, like during the session, the time just flies. I just was able to cover three, and we're done. I thought that we'll not go through the news articles and we'll not go through the code and documentation sessions. We'll only focus on the testing guide, but the testing guide also we could not finish. But at least whatever we covered, it's important that we covered it in detail and understand it instead of just rushing through the topics and trying to finish the topics without understanding them. You are welcome, Jayant. Right, those of you who have any questions can stay back and ask questions or type your questions in the chat section. Those of you who don't have any questions, please feel free to leave. Good night. Thanks a lot for showing up. Enjoy your dinners.